Alright, for this video we're going to go a little more in-depth into pulses and standing waves and resonance and sound and all that kind of good stuff. So first and foremost, if I've got a string, let's say it's fixed on one side, or both sides, when I send a pulse down, and let's say a transverse pulse, so the particles are moving at 90 degrees to the direction of the pulse, when it reaches the far end where it's clamped down, it reflects back on the opposite side. That's because this far little particle can't move up and down the way that its brethren did. So instead, because it's fixed in place, when the particles next to it start to move up and attempt to tug it up, it ain't going anywhere. That little bit of increased tension pulls the rest of them downward, and so it reflects back on the opposite side. So if I send an upward pulse and it hits the closed end, it comes back as a downward pulse. Now, the opposite's actually true once you have an open end, a totally loose end that's free to move up and down. If I send a pulse that time, then that free end just moves up and down, and everything's fine. It just comes back on the exact same side. If I start to send a series of pulses, then one of them might interfere with the previous one, and you get some sort of interference, either constructive if they're both on the same side, or if they come on opposite sides of each other, you get destructive interference there in the middle. Now, when you continue to send a series of pulses over and over and over again, and they continue to interfere with each other, you can get what's called a standing wave. And all that a standing wave is a series of pulses that constructively and destructively interfere with each other, all on one string, for example, or one column of air. And it makes a wave that looks like it moves back and forth from crest to trough, but it has no ultimate forward velocity. Now, the pulses themselves are moving back and forth across a string or the pocket of air or whatever's vibrating, but the overall wave looks like it's just moving from crest to trough and crest to trough. So as an example of this, I got a simulation up here where I'm going to grab a fixed end on one side, the other side will have an oscillator on the other. That'll be moving up and down, so I'll have one loose end and one fixed end. So at the fixed end, the pulses will come back on the opposite side of the string, so an upward pulse will come down to the downward side on the way back, and on the loose end, the reflection should just go back the exact same way. As they start interfering with each other, you should start to see a little bit of a standing wave there. That looks like it's moving backward, forward, but ultimately not forward motion of the pulse. It looks like there's not a single pulse that you can actually discern heading from the oscillator over to the clamp. So if I pause it at the right time, then I should be able to pick out what are called nodes and antinodes. A place where there is no movement of the particles, meaning there's always there's always destructive interference there at all times. We're always getting a pulse meeting a crest. Wait, a pulse meeting a crest? Whew, a crest meeting a trough. That's where I get a node. And that includes any fixed end that might be there. The regions of the standing wave where I'm getting the most constructive interference, it's actually shifting back and forth from constructive to destructive to constructive the other way, to destructive to constructive the other way. Those regions of the string are called antinodes. And once you've got all your nodes and antinodes labeled, it's actually really easy to tell how much of a wavelength is fitting on this length of a string. Between any antinode and the next antinode, there's always half a wavelength, for example, from crest down to trough. From one node to the next node, there's always half a wavelength. So if I wanted to go two adjacent antinodes over, that would be one full wavelength, and so on and so forth. Between every antinode and the following node, there's always 1/4 of a wavelength in there. So, those are just little helpful tools. So for example, let's say that this entire string I knew, for whatever reason, was 3 meters in length. And I wanted to know a little bit about the standing wave that's fitting on there. Well, in this particular example, I start at one antinode, I travel down to another antinode that's half a wavelength, the next one that's another half, so I've traveled one full wavelength. Down to yet another antinode, there's another half, so we're at 1.5 in total. And then I hop up to the next node. That's another quarter wavelength. So in total, I traveled 1.5 plus a quarter, that's 1 3/4 of a wavelength. So, for this particular standing wave, I could label the string two different ways. L equals 3 meters, and the same distance, that same 3 meters, equals 1.75 lambda, or 1.75 times the wavelength. So I could then go back and just write, well, 1.75 lambda equals 3. Set my two different types of labeling equal to each other, and ultimately, you'd be able to solve for what the wavelength of the standing wave is. And that's what's going to be really important when we come to resonant frequencies. So objects, depending on how they're made, if it's, I guess based on the material, the type of tension, the length of it, end up with natural frequencies. This is where objects easily vibrate, and not only do they easily vibrate at their natural frequencies, if they're driven by that same frequency, it'll amplify it like crazy. So if you think of pushing someone on a swing, if you push them a bit too early, they're just going to smack you in the face, and it'll actually kind of ruin their swing. If you push them a little bit too late, then you're not going to get a really good shove in. But if you push them at just the right time, they'll actually swing up a little bit higher. So you're pushing at the exact right resonant frequency for their swing. It's the same deal for any other objects like bridges or musical instruments. If you drive them at just the right frequency, that frequency will resonate. It'll filter out all the other frequencies that are pushing it, and then you'll find a resonant frequency. It'll either give out a nice tone at that frequency, or it'll vibrate, like the Tacoma Narrows Bridge. If you weren't in class that day, look it up. It's a bridge that vibrated at its natural frequency. It was actually in the second harmonic, and then it fell apart because it couldn't handle that sort of amplitude. Now, depending on whether the ends are fixed or not, you get different patterns of standing waves. So again, on every single fixed end, you get a node. On every single open end, you get an antinode. So, an example is a guitar. If I play a guitar, it's fixed down on both ends, and the standing waves that I can fit in there will go from one node to the next in the first harmonic, and that'll be it. That'll just be 1/2 a wavelength fitting there. But if it's in the second harmonic, then it'll still go from node to node, but it'll put another node right smack dab in the middle there. Well, that fits exactly 1 wavelength, and so on and so forth. Basically, the different harmonics are a way to get from one node on one end to the node on the next, with a certain number of nodes in between. The first harmonic has no nodes in between, the second has 1 in between, and the third has 2 in between, and so on and so forth. So in this case, I've got 1.5 wavelengths. So as the harmonics increase, my total wavelength, let's assume this is all the same length string guitar, the wavelength itself is decreasing, getting smaller and smaller, and the frequency to drive it is increasing. In fact, because the wavelength decreases by a factor of 2 from the first and the second, that means the frequency increases by a factor of 2. Same deal if it's open at both ends. Let's say like a flute. A flute has 2 open ends that you blow air through. You get antinodes on that side. So if I go from one antinode to another, I get 1/2 a wavelength. If I do it for the second harmonic, then I go from crest to trough to crest. That's 1 full wavelength. So it's the same sort of pattern for the number of wavelengths that are fitting in there. The special case is when you've got 1 closed end and 1 open end. For the very first harmonic, the fundamental, I go from a closed end. Oh, by the way, this would be like a trumpet. On one side of your trumpet, your lips are closing it off. On the other side, it's just an open bell. So I'd get a node on the closed side, I'd get an antinode on the open side, and I'd only fit 1/4 of a wavelength from a node to an antinode in here. The next harmonic up, I would fit, well, there's 1/2 a wavelength and another 1/4. So that'll be 3/4 lambda in there. Now I've not decreased my wavelength by a factor of 2, this time I've done it by a factor of 3. So for this reason, if you've got 1 closed end and 1 open end, you don't get any even-numbered harmonics. Because again, the definition of the second harmonic is a standing wave in which the frequency is 2 times the fundamental of the first. I don't get that with one open and one closed. The next harmonic up is the third harmonic because I've multiplied my frequency times 3. So that's just a general note. Now, to help me demonstrate a real-life standing wave, I'm going to need some help from my physics assistant, Starship the Cat. So, Starship will pin down her end of the string, creating a closed end, meaning there's a node right where she's holding it. Meanwhile, I'm vibrating the string at its resonant frequency. You can see a little node right in the middle, a spot where it's not moving. Meanwhile, on my end of the string, it's difficult to see, but I'm just holding a wand with it. So that's an open end of the string. It's not being clamped down at all. The wand is just shaking back and forth. So you get an antinode there. When I increase the frequency of the vibration of the string, at first you get a jumbled mess because a standing wave isn't perfectly fitting on the string, until finally you end up with an upper harmonic standing wave. So it's another resonant frequency, just a higher one. Ah. Well done, Starship. Good girl. Now, since we're moving into sound waves, where sound waves are just the vibrations of air, they travel at the speed of sound. The speed of sound in air you can always calculate just based on the temperature of the air. It's 331 plus 0.6 times T, where T is the temperature in Celsius. And that'll get you the velocity of the sound wave in meters per second. So sound actually travels faster on a warm day than a cool day. Fascinating. And I think that'll just about do it for today. Stay tuned when we talk beat frequencies and the Doppler effect. Mwahaha. Farewell.